So this is question 8. Now we are transitioning to the state space model. We've covered so far the frequency and time domain methods, and we've spent a lot of time on systems with delays. Now we look at the state space representation of a model, and then the state feedback controller. So we have a basic system which shares some poles with our initial system that we've used. Now, the first step here is to find the state space representation, and the second step will be to determine the state feedback controller, for example, that has to assign the poles to minus 3.5 plus minus j. So let's start with basic stuff. Now, we have a very basic transfer function, so it will be very simple and easy to convert this into a state space representation. So now let's first of all note our transfer function down. So it's s squared plus 7s plus 6, I guess. Yep, 7s plus 6. So now transfer functions are the Laplace domain representation of differential equations and our dynamic systems. We're dealing with dynamic systems. They should be linear, time invariant, and that's the only restriction we have for now. And the transfer function by definition is the relation between the output and the input, the only difference being that it is defined in the Laplace domain. So we have basically this here. So this relation can be used to acquire the differential equation. And most of the time, if we model systems, we will use differential equation and then convert them into the state space. But yeah, here we have the transfer function, so we need to go back to the differential equation first. So in order to do that, we will introduce another transfer function, which is called x divided by u, which is basically between a signal called x and the input. So, and here, for the sake of simplicity, I'll always use only the denominator of the transfer function and not the numerator. If this is 6s plus something else, for example 2, I will omit this part. I will just take this denominator and I will use 1 as the numerator. So this will always be the step in this conversion if you want to end up with the same state space model that I'll end up in here. So even if there's a constant 6, I will omit that. So now once we have this, we can just cross multiply everything in order to end up with this here. Since I have used 1, I can just have u on the right hand side, and then I have x times this polynomial here. So we can also expand this or distribute x on this parenthesis to get x times s squared or s squared times x plus 7s x plus 6x equals u. (6x) equals u. Now, since we are in the Laplace domain, and since multiplying with s corresponds to taking the derivative, and since the transfer functions are defined with 0 initial values, because the derivative, the x dt, for example, in the Laplace domain corresponds to s times x minus x0. So if you don't have any initial conditions, then it's just s times x. And if you do it twice, then you have the second derivative. If you do it 3 times, then you will have the third derivative, etc., etc. So what this basically is, this is x2 prime and then 7x prime and plus 6s equals u. So this is basically the differential equation that we are looking at. And now, since this is a second order differential equation, this is an ordinary differential equation, it's an ODE, And that's also the reason why in Simulink we choose ODE solvers. Now, the state space representation is very close to this differential equation with only one difference, and the difference being that we never have high order derivatives in state space models. So we have to come up with a way of reducing the order of the differential equation into a first order one. But since we have multiple derivatives or high order derivatives, this will lead us to multiple first order differential equations. And if we put them into a matrix notation, then that's it. That's basically the state space representation that we are after here. So the way of converting a second order or nth order differential equation into a state space model is as follows. You take the constant term here, the one that has no derivative, and define it as a new variable, let's say x1, since we will have multiple x's in here. Now, if you take the derivative of x1, then you have a new variable, and we will call it x2. We will assign this to a new variable. Because we want to reduce the amount of derivatives, the order of the derivatives, we each time we have a new derivative, we assign it a new variable. So therefore, we will then have x2 dot. But at this point, I have to stop because, let me use this comment here, this is x. Now this corresponds to x derivative, but this will correspond to x2 prime, or the second derivative of x. And my differential equation ends here. So therefore, I cannot introduce new variables because I don't have other high order derivatives. So I should stop here and use x2 in my equation. So I can go back to my initial ODE, and I can start substituting the new variables into my old equation. So I have, instead of x2 prime, I can use x2 prime. And instead of x prime, I might go ahead and use x1 prime, but that would not change anything. But I can also get rid of the prime by using x2 because they are equal to each other. So instead of 7x1 prime, I can use 7x2. And that's basically it. X was x1. And now, as you can see in this equation, in line 16, we don't have a second order derivative or higher order derivative. There's just one derivative, and that's basically x2 prime. But then the question would be, what about x1? Because this is obviously related to x2. What about x1? So therefore, we have another equation, a hidden one, which is given in line 13. If we combine these two, we can see that for certain x1 and x2, this equation can be solved. Because u is a known signal, hopefully. Maybe it's 0 if you look for the unforced response here. And then we will try to figure out what x1 and x2 is. Therefore, we need the derivative of x1, if this is a differential equation, and then the derivative of x2, and that's basically it. So by using line 16 and 17, we can model this differential equation, or the transfer function defined in here. So now, I've talked about the matrix notation. Let's switch the order here. Now, about the matrix notation, it seems like we have derivatives on one side, and then the algebraic equations on the other side. So what we can do is we can rearrange these. Let's get rid of these. So they should have negative sign. These are the algebraic ones, and these are the derivatives. So I have reorganized it, and if I work on it a little bit more, let's swap the spaces here. Let's have this one here. There we go. Now I can define some notation here, namely dx, which could be x1 derivative and x2 derivative. And then I would have x, which is basically x1 and x2. And then I can model this as dx equals dx equals something times x plus something times u. Now here, obviously, we have two lines. Therefore, we can use a matrix notation, and this does not rely on x1, so this should be 0. And 1 times x2, therefore this should be 1. And then to the next line, we have minus 6x1 and minus 7x2. And there we go. Now, if we want to add this and this, we have to have a 2 by 1 vector here, because this is 2 by 2 times 2 by 1, which gives 2 by 1. So dx is also 2 by 1. So u is a scalar because it's a scalar input. We have to have a 2 by 1 vector here. So the first equation does not have any u. This doesn't mean that I don't have, I can't use the notation. Of course I can. I can use it like this. 0 times u, 0 times x1. Then I have the entries 0 and then 1 and then 0. So this should be 0. And then minus 6, minus 7, and then 1. And that's basically it. So of course, I'm not going to write it like this. I'm going to name the first matrix here A, and the second one, the second vector in this case, B. So this will be always dx equals ax plus bu. So therefore, A is this matrix here. And then B would be 0, 1. Let's get rid of everything here. Maybe this should be like this. So, of course, this is the notation. We have acquired the dx equals ax plus bu part, which is basically corresponding to this transfer function. But the problem is that our output y is not defined yet. So what about that? How can we get the output equation here? Because this is basically the internal signal, x, which is not the output that we're after here. Luckily, we have this transfer function definition, and we got rid of this 1 divided by, so this is basically 6 times this, and we've already transformed this into our model. So what we can do is we can just multiply everything with u, or we can just say that this is basically x divided by u. So therefore, there's a relation between the transfer function that we want to achieve and the transfer function that we've got at this point. And there's a static relation. Multiplying with u or getting rid of the u's shows us the static equation that we need. And I can generalize it with 0 times u. So therefore, I can say that I have 6x plus 0u. Of course, x was x1 by definition. So this would be generalized into this here. So there's no x2, no u, and 6x1. And that's it. So at this point, these will be called C and D. So C is equal to 6, 0. And then D is equal to 0. And that's it. We have the state space model. And our state space model looks like this. Y equals Cx plus Du. So we can get rid of everything else. We've basically transformed our transfer function into a state space model. Now, what about 6s plus something else? Let's say 6s plus 2. What would be the state space model of such a transfer function? Now, if we plug this in, we can still use the same trick where we assume that this is basically separated like given in line 17. Now, I've already worked out that this is x divided by u, and if I multiply with u, I will see that this is basically it. Now, we've already mentioned that we can use this, and multiplying with s is basically the derivative. So this is 6x prime plus 2x. Now, I know what x is, that's x1, and x1 prime is the next variable called x2. So therefore, we have y equals 6 times x2 plus 2x1. So the C matrix for this would look like 2 and 6, not 6 and 0. So that's basically it. So what about a biproper version? What about s squared plus 6, or let's say 4s plus 3 divided by this part here? Now, this will basically be the same. The only difference here being the only difference will be here the following. We would just have to come up with a constant ratio between s squared plus 4s plus 3 and then s squared plus 7s plus 6, which is obviously 1. So I can transform this into, let's say, ms plus n divided by the denominator here. So you can do this, you can just multiply everything with this, because we want to have this equation here. So if you multiply with this, you can find out what m and n is, and then you can repeat the steps and come up with the C matrix. Obviously, this part here will be D. So D would be equal to 1 in this case, if it's biproper, because the direct coupling is equal to 1. So here we can see that dividing by u gives us C times x divided by u and D. So if there's something between y and u as a constant term, then that's D. So that would be D. So now let's try to validate this ABCD state space model, and we can achieve that by, let's say this is GS. Let's get rid of this. Now we can do this by using the general notation that I've introduced just now, Cx plus Du. Now keep in mind that ABCD are matrices, and that's the only information that we need so far. So let's attack this equation. We can take the Laplace transform, because now we start from the differential equation or the state space model, and we want to transition into the transfer function, so we have to use the Laplace domain. Now, since dx in the Laplace domain would correspond to s times x equals ax plus bu, this is basically straightforward. Even if the dx is a vector, you can do this element by element, so no problem there. The only thing that you should note that is that this should be s times I times x in order to be able to carry out this multiplication. So now I can rearrange this. I can take ax and put it in here, and I can also factor out x here, and the ordering is important. Keep in mind that this is on the right hand side, and minus b plus bu is not what it should be, so this is bu. Now I can take the inverse from the left, so this inverse times this equals this inverse times bu. Of course, this will vanish because I multiplied with the inverse, so this would be like this, and I can also divide everything by u. So I kind of worked out the x divided by u, and if you remember, I started by using the denominator, 1 divided by the denominator, and I've defined that as the transfer function between x and u. So I'm doing the same here. Now we're good to go with this part. We're done with this part. Now we have the second equation, which should give us another relation, and that should result in the transfer function, hopefully. Now I can convert this into the Laplace domain, and if I divide by u like this, we get this relation. Now you can see that the transfer function between x and u is present here. I can copy this. And we also have x and u, and we are trying to determine what y and u is. So if I plug this in, I have the transfer function defined. So there we go. Now this tells us the following. If we multiply C with the Si minus A inverse matrix, and then with B and add D, we would get the transfer function back. So let's try this out. Let's define the symbolic S. And since we have A, B, C, D, the only thing that we should do is GSS should be equal to C times the inverse of S times the identity matrix. And this depends on the size of A, and since we have a 2 by 2 matrix, we can use this. So C times S times I minus A, the inverse of that times B plus D. And that's it. So let's leave this one and get rid of all the other stuff here. Maybe we should use simplify on this and then pretty. Of course. There we go. We started with 6 divided by s squared plus 7s plus 6. We converted it into state space, and then we converted back to the transfer function that we started with. Now, using this expression here, we can always get the transfer function, and we will always get just this transfer function, nothing else. But if we use this transfer function and we want to get a state space model, there are infinitely amount of possibilities, for state space models. This is not the only way, and this is not the only result that we can achieve. And it would be changed if I use, for example, 2 divided by the denominator and then 3 times that. So that might be one of the possibilities. Since you can mess with this multiplication, it should only result in 6, and that's the only difference. You can separate it as you wish. It will give you different state spaces, but all those state spaces will result in the same transfer function if you use this relation here to convert it back. So that's quite nice. And I guess I can demonstrate it if I, for example, change B and C. Now let's multiply this with 2 and let's have this, for example. Now what happens if I repeat this with different B and C? Now as you can see, same transfer functions, but here I have a different B and C matrix, here I have a different one. And that's not the limitation here. I can also have 3 by 3 systems, and 3 by 1 vector here, 1 by 3 vector here, and still have the same transfer function. So, yeah. Now, this was the first part of our question, and the second part was to design a state feedback controller. Now, the state feedback controller is designed pretty easily, and let me show you how. Let's say state feedback controller. Now, the poles that we need to assign to were minus 3.5, I guess, plus I, 1i, and then the conjugate. Let me check. So, yeah, 3.5 plus j and minus j. Those are the poles. Now, here we will utilize the Ackermann formula. And there's also a command for it, Acker. But I will show you the formula itself, because if you have only pen and paper and calculator available, you won't have MATLAB, so Acker cannot help you or place. So let's see. Now the state feedback vector k can be acquired with and I'm going to write for a 2x2 system, this times the inverse of the controllability matrix times something called PDA. But here PDA is basically PDS, and we should substitute into PDS s equals A. And you remember what PDS is. PDS is basically, and for this example, it should be S plus, or S minus in this case, S poles 1 times the other one, this here. Or we could also use the sum and products of this. So A should be the sum of the poles minus, as far as I remember, and then B should be the product here. So prod of poles. Let's see. So let's first of all calculate this. Now A is 7 and B is 13.25. And the roots of 1A and B gives us again the same, as you can see. So PDS is basically, and it makes more sense to write it like this because of numerical sensitivity, A times S plus B. So this is PDS. There we go. Now, since we have an A matrix, we should substitute this A matrix into this one. Now, of course, this seems a bit odd, but it has its reasons, and the Ackermann formula was derived because of the fact that the inverse of a matrix, or the matrix itself, satisfies its own characteristic equation. So that's basically a part of the proof, which I'm not going to dive deep in here. But if you're curious, you may look it up. So yeah, it's quite interesting. And there's also a relation between the inverse. So we can get using the characteristic equation of the matrix, you can get an expression for its inverse in terms of its self. So yeah, instead of using A inverse, it becomes sometimes handy. What you can do is you can use determinant of S times I minus A. And since this will be satisfied by A, you can work out your inverse formula. And it would be something like A plus 2I, for example. So it is quite used in many areas. So whatever. Now, therefore, we have to substitute this into its own equation, sort of. But since our closed loop should satisfy this PDS, the part that remains is basically the open loop part that should satisfy PDS. So hope that it makes sense. But you can also skip that part and just remember this formula, this Ackermann formula. It's up to you. Now, we have PDS. Now, I guess I can use a little MATLAB hack here, but I'm not sure. MATLAB function PDS gives me something like this, which is not the same for a matrix. So, yeah. Well, we have to do it manually. So, since this is PDS, PDA is equal to A squared plus A times capital A plus B times identity 2. This is basically the expression of PDA. So if you, for example, have these poles, PDA should be equal to 7.25 and 7.25. This is diagonal by accident. It doesn't have to be, but for this one it is. And yeah, we have PDA. Now, so far we have calculated PDA, which is pretty much straightforward. We have used the poles that we want to assign to, and then we have worked out, since these are just two poles, we have used the product and sum, and then we've created our polynomial and then substituted the open loop A, basically this A, into it. And that's it. Now, what is phi c? This phi c is basically a controllability matrix. And the controllability matrix is constructed using A and B, and it looks like this. And the generalization would be a to the power of n minus 1 times b. And that's basically it. Now, since this is a 2 by 2 and 2 by 1, you will get a 2 by 1 vector, and this is a 2 by 1 vector, so they should be side by side. So I've also defined this one. Now, if let's get rid of this, I guess. Yep. Now, if I use these phi c, if I take the inverse of it, times PDA times this vector, this should give me the state feedback controller. So let's try. Now, capital K is equal to 7.25 and 0. Now, nice. Let's see if this works or not. Now, remember that dx was equal to ax plus bu and y was equal to cx plus du. My state feedback controller, as the name implies, will be used like this. Now, I need the states of the system, which are denoted by x. Those are the states of the system. I need to feed them back by using a sort of a generalization of p-type controller, because this is a vector, so there are p-type controllers for each state. That could be the way of thinking that we can use here. So I have two states for the system, x1 and x2. I assign each state a p-type controller. But this is not the usual feedback. This is a bit different because we don't have any reference signal embedded into the signal that we are using. So instead of E, you can see that instead of the error, we use the state itself. So the only difference lies in here. So then if we have U equals Kx, I can substitute this, and I can also use U equals Kx plus R in order to have sort of an influence to the system. So this would be then the reference, then this would be the state part here. So if I substitute this into these equations, I get the following. Now, of course, get rid of these parts. Now, we can see that this is basically, if I expand it, the result. So there we go. Now, I can use these here because they are multiplied with x. And the same goes for this one. And there we go. Now this is another system, another state space model, where my A, let's say closed loop, is equal to A plus BK, and my B is equal to B, it doesn't change, and CC, so the closed loop C matrix, that's only affected here, is C plus DK. Now the controller affects the system matrix A and the state to output relation C, and that's it. Now I can go ahead and define my state space models. Now it is possible to use SS, which is a MATLAB version of state space model, and we were using TF, so transfer function TF and state space SS. So basically that's it. So I can go ahead and use SS and A plus BK as the A matrix, so it requires the matrices. B was again the same. We used C plus D times K. Of course, there should be an asterisk here for multiplication. And then we have D. So this is basically the closed loop. So this is the closed loop. We also have the open loop. So we can also define our open loop A, B, C, and D. So let's suppress the output here. Am I displaying it somewhere? I guess I am. Let's see. Okay, pretty puts the output even if you have a semicolon. Okay. So what is TS or even? So here we have A, B, C, and D. Of course, this doesn't make much sense, but what about the transfer function? So Of course, you can again use the symbolic version here. You can use a plus bk for this one and then c plus dk for this one. Or you can also, in our case, use MATLAB here to convert it into a TF object. Now, of course, we have forgotten to use a minus here, which depends based on your usage. So this is TS now, and this is the transfer function that we want to have. Now you can see that A and B are the coefficients here. So this is basically PDS. So we had PDS. This is the same here. 13.25 is 53 divided by 4. So it is interesting to see that using a state feedback controller, I have assigned the poles to a certain point. But for this example, and this example only, I can see that my open loop transfer function had also a 7s here. So if I would have used a p-type controller, I could have gone away or got away with this, because I don't really assign the second part here. So using a certain p-type controller, I can basically assign to these poles. But what I can't do is the following. If I change this, for example, let's have -4 plus I for some reason, and -4 minus I. Then, if I look for the transfer function, I get a totally different one. Now, that's not achievable with a p-type controller. The only way of getting this result is to use maybe a PD-type controller, because it will affect the constant term and then also the S term, because Kp plus Kds will be present in the closed loop characteristic polynomial. So therefore, the state feedback controller can assign to any point on the S domain freely. The only restriction is that you have to be, or phi c should be invertible. If you have this inverse, if it's possible to invert this matrix, then you can assign wherever you want the poles of the closed loop. And this restriction corresponds to the controllability of the system. If the system is controllable, you can assign wherever you want. If it's not, then you cannot. Now, a weaker definition would be the stabilizability, which means that if you can't assign or can't take the inverse of this, then you try to assign some of the poles, but you hope for the other poles to be in the stable region. For example, if I'm trying to assign poles to -4 and -5, and the system is only stabilizable, then let's say I can assign to -4, and if I do this, the system internal mode that I'm not reaching with my controller should be stable on its own. If that's the case, then I'm good to go. If, for example, I cannot affect the second pole, which is placed at s equals 5, then I cannot control the system. It's not even stabilizable, so nothing much to do there. So, yeah. Let's conclude the question here. I didn't look for the closed loop step response because that was not a requirement here. You can see step by step that we use x and u, the transfer function, the dummy transfer function, for if we want to name it like that, and we cross multiply everything and then define x1 dot and x2 dot, and we have the matrix notation here. So converting it back into the Laplace domain or transfer function here, we can use this relation. And you can see that there's a matrix inversion here and also some vectors to reduce this down to a scalar one, scalar expression, and then we get the transfer function back. So now here we can see the calculation of PDA basically. Therefore, we have to shape our closed loop polynomial, the desired closed loop polynomial, which we all have used many times in control design, classical controller design. And then we get the polynomial and we use the matrix, plug it in, and we get basically PDA, one part of the Ackermann formula. The other part is about the controllability, and the nice thing about the formula here is that it includes the controllability of the system. So, by the way, if you use minus sign here, you can use A plus BU, or U equals KX. If you don't use it here, then you have to use minus KX, so it depends on you. Which one suits you is the best, then use that one. So, this concludes this lesson.